Hi everyone. For the colligative properties and the remaining of your slides, I took off all of the slides that had to deal with colligative properties and just made a handout explaining the 4 different ones that I'll want you to know. If you have questions on that handout, then email me or post on the blog and we can talk about them. Since we had the snow day today, remember that your first introductory part of the lab, where we'll run a couple different versions of chromatography strips, will be tomorrow, and then you'll still have your test on Friday, and then Monday we'll do the guided inquiry part of your lab. So this slide I'm not going to talk about because it's part of that handout, and we're going to get into just a couple other things that maybe deal with a little bit about colligative properties, but then ultimately we're going to end the PowerPoint with colloids. All right, guys, so we've talked about vapor pressure quite a few times, and again, we see it popping up in our solutions chapter. So we know that vapor pressure is simply just a dynamic equilibrium between molecules that are leaving the liquid phase entering into the gas phase, and then also the gas particles leaving the gas phase and entering back into the liquid phase. So that's how we define vapor pressure. But what about if we have vapor pressure for a solution? So maybe instead of just thinking about it of a solvent, now maybe I have it for a mixture of particles. Usually when we have a solution, the vapor pressure of a solution will be lower than that of the pure solvent. A substance, we have two different colors of particles here. You have blue ones, which are representing volatile solvent particles, and then you have the red ones that are representing non-volatile solute particles. I would like you to know that volatile means that it's easily evaporated at normal temperature, and then non-volatile means that it does not tend to vaporize very easily at normal conditions or normal temperatures and normal pressures. Okay, so let's say that we add non-volatile solute particles. So before I just had solvent, now I'm here, I've added some non-volatile solute particles. I'm going to see that the rate of vaporization is going to be reduced just because I have just because I've added more solute particles. We have the presence of more particles, so that's going to change the strength of those intermolecular attractions. It's going to make it harder for the remainder of those solvent, the blue particles, to get up into that gaseous state, because maybe this red non-volatile solute particle here is blocking the way for this one to move up into that gaseous state. So just because we've added more solute particles, or just because of the presence of these solute particles, we're reducing our rate of vaporization. So we have to establish a new equilibrium with fewer molecules. We can see that here in the gas phase. So that means that our vapor pressure in terms of a solution is always going to be lower than that of a pure solvent. All right, guys, so we have another law that we need to learn about in terms of solutions, and that's called Raoult's law. Raoult's law states that we can calculate the partial pressure that's exerted by a solvent vapor above a solution, and we can do that by taking the mole fraction, because remember that X sub A is representing the mole fraction, and we're going to multiply that by P with a little degree sign sub A. This P with a degree sign is just stating the normal vapor pressure of that particular compound at a specific temperature. So Raoult's law is really just a way that we can try to account for the fact of getting a more accurate pressure based on the number of moles that we have in a solution. So Raoult's law will be followed by ideal gases. We know that in ideal gases, we know follow ideal gas law. If we think about an ideal solution, then an ideal solution is going to follow Raoult's law. So think of this as kind of like that For the ideal gases, we know that if it goes to PV equals nRT, that's really important because that means that it will follow that ideal gas. So same thing here. If we have an ideal solution, then we'll have it follow Raoult's law. One other thing I think that I just want to add with this is that an ideal solution would be one where we have total uniformity of interaction. So the strength of those intermolecular forces throughout my solution should be equivalent. They should be equal to one another. I should have uniformity throughout. I could also say that in the way that all molecules that are in a solution are going to influence one another in the exact same way. Okay, so you'll have to look at your handout to look at those 4 different types of colligative properties. Remember, we had boiling point elevation, we had freezing point depression, we had vapor pressure lowering, and we have osmotic pressure. We can also talk about colligative properties for electrolytes. So it says, since the colligative properties of electrolytes depends on the number of particles dissolved, solutions of electrolytes, which we know just those ions are dissociating in solution, so that means that I have ions that are present in a solution, should show greater changes than those of non-electrolytes. Of course, there's a problem with that in that one molar solution of sodium chloride does not show twice the change in freezing point that a 1 molar solution of methanol does. So, the extent to which electrolytes dissociate is something that we call the Van 't Hoff factor. Okay, sorry guys, Stace and I are at Panera and it's a little loud in here. So the Van 't Hoff factor just means it's the extent to which electrolytes are going to dissociate. Now, if we're looking at this representation, I see that it says 1 mole of sodium chloride in water does not really give rise to 2 moles of ions. I have a chloride ion here, I have my sodium ion there, but all of these are surrounded by those water molecules, so we really just see them or experimentally have found them to be acting as 1 ion pair. So in a solution, some of the sodium ion and some of the chloride ion will end up reassociating for a very short amount of time. So the true concentration of particles is actually somewhat less than 2 times concentration of sodium chloride. So what we'll see here in our diagram or in our representation here, as the ions start to move around in the solution, the ions of opposite charges, so I have my chloride ion, my sodium ion, they're going to end up colliding with one another, and ultimately they're going to stick for a couple brief moments because they have that Coulombic attraction. While they're together, they're going to behave as a single particle, and that single particle is what we'll just call an ion pair. Now, of course, the water molecules will again pull them apart and try to solvate again so that way they can fully surround them. But now, because for a moment these will come together because of Coulombic attraction, because they're colliding, and they'll stick, then now the number of independent particles, the number of those ions that are free, is now reduced because now we have this ion pair. Okay, so continuing with this Van 't Hoff factor, reassociation, so when we have an ion pair that's formed, or more ion pairs will form at higher concentrations. That's just because we have more dissolved in a solvent, so I have more solute particles at a higher concentration, so then I'm more able to get more collisions with ions forming ion pairs. So the number of particles present is concentration dependent, and we can see that in table 13.4 to the right. So on your colligative properties handout, you'll see that for boiling point elevation and for freezing point depression, you have ways that we can find temperature and how much these colligative properties will affect either boiling point or freezing point. So we have to modify this then based on concentration, and this is what we call that Van 't Hoff factor. So after you've looked at your colligative properties handout, you'll see that instead of just saying our change in our temperature here, whether it be boiling point or freezing point, is now equal to that Kf times this effective molality times I, and I is represented by this Van't Hoff factor. So now we're taking into consideration how many ion pairs we're really having together now, and thinking about that now we can get these ions that should be dissociating into a solvent, but sometimes they're going to be able to stick. So this I is just now calculating in that factor. Guys, our last thing we need to talk about in our solutions chapter is our colloids. Colloids are just suspensions of particles that are larger than individual ions or molecules, but colloids are too small to be settled out by gravity, so it's really hard for us to see that. And a table of just some examples of different phases of colloids or different types of colloids is here in table 13.5. So you can see here that we have fog and smoke, milk is an example, butter, marshmallow, paint. You know that blood is another example of a colloid, but you have these different phases of colloids. So remember, we have what we call the dispersing substance and the dispersed substance. So the dispersing substance is really acting like the solvent, and the dispersed substance is going to be more like the solute. So I could have a gas dissolved in a gas. I could have a liquid dissolved in a gas. And a type of that would be like an aerosol. I could have a solid dissolved in a gas. A gas could be dissolved in a liquid, so that would be like, we could think about that as foam. Whipped cream would be an example. A liquid dissolved in a liquid. We just have liquid butterfat that's dissolved in water, which makes milk. Another name for that is just an emulsion. We've heard this before, the colloid type Sol. So that's where we have a solid that's dissolved in a liquid, so paint would be an example of that. And then we can just continue on through the list. We also spoke last year about the Tyndall effect. So we know that colloidal suspensions will be able to scatter rays of light. And just this effect all on its own is called the Tyndall effect. And consequently, most colloids, because of this, usually appear cloudy or opaque. And that's because they're able then to scatter rays of light. And there is an exception to this, and that would be if the colloid is incredibly dilute. But that'd be something that we would have to kind of force for that colloid. So usually when we see a colloid, they appear very cloudy or opaque. Guys, for us, the most important colloids are those that have a dispersing medium in water. So the dispersing medium is water. We have some molecules that have a polar end, and then there are some that also have a non-polar end. So the molecules that have a polar end we call hydrophilic. And hydro just meaning water, and then the philic meaning loving. So hydrophilic just represents water loving. A non-polar molecule, a molecule that has a non-polar end is something that we call hydrophobic. Hydro meaning water, phobic meaning hating. So hydrophobic is just translates to water, water hating. In the human body, we are made up of very large molecules, and a lot of these large molecules make up enzymes and make up antibodies. And a lot of these enzymes and antibodies are kept in suspension by interacting with surrounding water molecules. What ends up happening is that a hydrophilic molecule will fold in a way that its hydrophobic groups will end up staying away from water. And think about why. If hydrophobic means water hating, then that end of that molecule is going to want to stay as far away from water as possible. And then the hydrophilic groups, the water-loving groups, are going to end up being more on the surface if water is closer to that surface, because the hydrophilic water-loving groups want to interact with the water. So hydrophobic colloids can be dispersed in water, so it can happen. We can have hydrophobic colloids in water, but that's only if they're stabilized some way. One way to stabilize these hydrophobic particles that are in water is adsorbing ions on the surface of these hydrophobic particles. So we can do this by something called adsorption. Adsorption means to adhere to a surface. So the adsorbed ions can interact with water. So we have here in our water, we have two hydrophobic particles here. We can have adsorbed ions that can interact with this water. So we can actually adhere ions to a hydrophobic particle to try to keep it stabilized in water. Another way that we can stabilize hydrophobic colloids in water, we can also stabilize them by adding on a hydrophilic group on their surfaces. So oil drops are hydrophobic and they will not interact with water. But we know that there's a compound called sodium stearate, which is, we can see that stearate ion. The stearate ion is right here, and we just have our sodium cations around here. Sodium stearate will stabilize a suspension of oil in water. Sodium stearate is just a very large molecule. So we see that here, that stearate ion. So we have a really large hydrophobic end. So it'd be like a big, long hydrocarbon chain. But it has this one little tiny hydrophilic end here at the very end of that molecule. So how does it stabilize? Well, the stabilization results from the interaction of the hydrophobic ends of the stearate ions with the oil. So here's my giant oil drop. And my stearate, the hydrophobic version, or the hydrophobic part, that carbon-hydrogen chain, is going to interact with the oil drop. That polar group, that water-loving group, or hydrophilic part, is going to interact more with the water. Because of this, we can stabilize then that oil droplet in water, because now we have these polar groups that are interacting with that sodium ion that was part of sodium stearate, and it stabilizes then the oil droplet in water. Lastly, continuing on thinking about how some molecules have a dual nature. They can have a polar head and they can have a non-polar tail. We know that the polar head, the polar version, or the polar side, will be dissolved by water, and then the non-polar tail will be dissolved by something else that's non-polar in nature, so like oil or grease or something else. Soaps and detergents are synthetic things that we often make that involve some type of sulfate group. So you can see here that this is a soap, for example, we call SDS, so sodium dodecyl sulfate. That soap has this really long non-polar tail, but it has this other small end to it that has the polar head. Ultimately, what will happen is that individual soap molecules end up congregating around some oil molecule or some grease particle, and they form something that's called a micelle. And we can see that the hydrophobic, so meaning water-hating ends, are going to be around that grease molecule, that grease particle. And then the hydrophilic, the water-loving, or that polar head, would be surrounding then the part of the water. So ultimately what happens whenever you have dirty hands, or if you have greasy hands and you add soap to them, soap is going to lower the surface tension of water. It does that by interrupting the hydrogen bonding in water. So soap micelles in water aren't really dissolved in water, but they're just dispersed as a colloid. So our soap or our detergents act like colloids in water because they're forming these micelle type shapes, and they're disrupting that hydrogen bonding network in water. So they're just lowering the surface tension.